In this video, we're going to look at an introduction to Laplace transforms. And in the next couple of videos, we will look at how they are used to solve differential equations. But in this video, we're going to talk about kind of the idea and how they're used in this course and the definition. We'll look at a couple of examples using the definition. All right, so how we're going to use them in a differential equations course is that we're going to start with some kind of differential equation that for some reason is difficult to solve. And not every difficult differential equation can be solved using Laplace transforms. There are some properties that we'll look at with some theorems that kind of tell us when this is an appropriate method. So I wouldn't necessarily use Laplace transforms on one that we have some kind of other method already for. Sometimes the difficulty, and what we'll see particularly in this chapter, is that that difficulty might be that we have some kind of discontinuous forcing function. So some forcing function that is applied to our system and then it is switched off. So a discontinuous forcing function might be a reason why that might be difficult to solve using what we've talked about before. And then the idea is that we are going to apply a Laplace transform to our differential equation, and that will take us from what's called a time domain, where the input for our functions is t, time, to a frequency domain. And so that might give you some idea about other applications of this, but to a frequency domain. But essentially what that's going to do is that that's going to transform the equation often into an algebraic equation, or at least a simpler differential equation, but often an algebraic equation. We have a lot of tools in algebra, and so many of the problems that we're going to work with will be in an algebraic equation sort of realm. We'll have different letters because instead of being in a time domain, the differential equation has t as its independent variable. Once we've applied that Laplace transform, we'll be in a frequency domain, and commonly s is used for that. I don't like s because it looks like my fives, but that's what's used, so we just have to get used to it. But some algebraic equation where the independent variable is s. And the idea there is that for an algebraic equation, at least, we have more tools, so maybe that is easier to solve. And so we'll solve the algebraic equation and get a solution for that. And then we want to go back to this time domain, this differential equations realm. And so we're going to need to undo our Laplace transform. So we will apply an inverse Laplace transform, and that will take us back to a solution of our differential equation. And so there's a lot of other notation besides what's in this picture here, and there are a lot of uses of Laplace transforms besides what I've described here in this picture, but that's essentially how we're going to use it in this course. Occasionally, when we apply that Laplace transform to some of the differential equations we will work with, instead of an algebraic equation over here, we might actually have a simpler differential equation than the one we started with. But it will still be in this S or frequency domain. All right, so let's look in this video at the definition of the Laplace transform, and we will look at a couple of examples using the definition. All right, so that is typed. This is from our class notes. That's typed down here below. So we have some f of t function, little f of t, defined for t greater than or equal to 0. The Laplace transform of little f of t is given by, and when you see it typed, you'll see some sort of script L. Depending on the font that's used, it might look like that's L that's typed when I handwrite it, or sometimes when you see other fonts and other text or whatever, you might see it written more like a cursive L with a little loop at the top, but that sort of script L indicates the Laplace transform of something. Other common notation that you should note there is these brackets. So when we take a Laplace transform of something, it's common to use those braces there, those curly brackets, instead of parentheses or some other kind of notation there. So that would indicate Laplace transform of little f of t. And notice here, I talked about up in that diagram above that we start out with t as our input variable, and after I apply that Laplace transform, I get s as the independent variable. And then the definition of that Laplace transform is an integral, a definite integral, but an improper definite integral. Notice this upper limit of integration here is infinity. And there's several letters there in that integral, so it's important to pay attention to that differential at the end, right? So you're integrating with respect to t, so that s at that step is really being treated as a constant. So those limits of integration are from t equals 0 to t approaches infinity. And so we'll have to remember a little bit about some integration skills and about some improper integrals in order to use that definition. And then the last part of the definition there, it says, for all values of s for which this integral converges. So if you remember very much about improper integrals, you might remember that the integral might converge or diverge, and that has to do with the value of the appropriate limit that you take when you evaluate that integral. So we'll look at that as we look at a couple of examples here. We're just going to start off with some very basic functions and use the Laplace transform definition to find Laplace transform of these two very basic functions. So remembering that c is a constant, so Laplace transform of c, so notice my notation there, the script L and the braces, Laplace transform of c is equal to, and I'm just going to write down that definition as it's typed up above, the integral from 0 to infinity of e to the negative st, and in this case our function is just c. So I'm going to put c where the f of t was in that definition, dt. All right, so now I need to think about how to evaluate this improper integral. And so here's a little review of improper integrals in case you have forgotten that. So when you have an improper integral, it's improper because this limit of integration is not a number, it goes off to infinity. So the way that is defined is as a limit. So that is defined to be a limit as, I'm going to replace my upper limit of integration with a letter here, some letter that's not already in the problem. Usually we use a and b, but really you could use whatever letter you want as long as it's not already used here in the problem. So I replace that infinity with b, and then I'm going to out front here write the limit as b approaches infinity of this integral. All right, so limit as b approaches infinity of the integral from 0 to b of this integrand that I have here. I'm going to put the c out front since it's a constant. We're kind of used to writing that out front. All right, and then I need to go ahead and evaluate this integral. So remember that c is a constant, but it can take on lots of different values. So I have some sort of different situations here. If c is 0, notice that this will just be the integral of 0, which is 0. So that's kind of a special case here. So the Laplace transform of 0 is 0. But c could be lots of other values that aren't 0, so let's go ahead and calculate it for those other values as well. When I do this integral, I'm integrating with respect to t. So maybe you can think through, there's a little u substitution there. You would let u equal the exponent, negative st, and du would be negative s dt. And you would like to divide by s there so that you can finish that u substitution. So provided s isn't 0, you can do that. I'm going to go ahead and do that and just write s not equal to 0 out to the side of that. Okay, so I did the u substitution. I didn't actually write it out, but I simplified it and then I did the integration there. So the c can come out front because it's constant, and I would end up with, in place of my dt, du over negative s, that's where my negative s out here comes from, and then I'd have e to the u, integral of e to the u is just e to the u. All right, so I didn't actually write out all that u substitution, I just thought about it enough to be sure what extra factors I might get out front of my integrand here. All right, and so now I need to evaluate the definite integral from 0 to b. So I'm plugging 0 and b in for t. Remember that we were integrating with respect to t. So those values were t equals 0 to t equals b. And at the end, I'll need to evaluate my limit. All right, so e to the 0 is 1. So that last term is just c over s. So I need to think about this limit of the first term as b approaches infinity. And what happens to that as b approaches infinity is going to depend on the sign of s. All right, so we're going to break this down into kind of two separate cases here. If s is bigger than 0, so s positive, the negative sign that's in front of the s in that exponential function then will force this to be an exponential decay function as b approaches infinity, and that first term then would approach 0. That integral converges. Up here also, that integral converges. All right, and if s is negative, then my e to the negative sb term, if s is negative, there's a negative sign in front of s in the exponent there, and so that term will approach either positive or negative infinity depending on what c is, depending on the sign of c. But that integral actually diverges. So when we talk about an improper integral converging, that means it approaches a value and not infinity or negative infinity, or the limit does not exist. All right, we have one more thing to consider. We talked at the beginning about what happens if c is equal to 0, right? But the other situation that we need to think about is what if s is equal to 0. And so I'm actually going to have to go back a couple steps to think about what happens if s is equal to 0. At the step where I wrote s is not equal to 0, that was the step where I had divided through by s. And so I'm going to have to go back to the step before that and think about what is that value of that integral if s is equal to 0. And then I'm going to think about s being 0. So if s is 0, then I just have e to the 0 there. So that whole part is 1. So I just get the integral of c. And so I will get the limit as b approaches infinity of ct evaluated from 0 to b. So I will plug in 0 and b. So I'll get cb. And again, this limit is either going to be infinity or negative infinity, depending on the sign of c. And again, remember, we already considered the situation if c is equal to 0 up above. So depending on whether c is bigger than 0 or smaller than 0, in this step, though, that limit will be infinity or negative infinity, which means that integral also diverges. All right, so what we can say over here, after all this work, is that the Laplace transform of 0 is 0. We kind of calculated that as a separate case. And the Laplace transform of c is c over s for s greater than 0. Okay, so what does that mean? Well, how that helps us is that when we take Laplace transforms of differential equations, whenever we have constants, this is what we're going to get. So again, going from that time or t domain to the s domain where we've taken the Laplace transform, this is what we get. We will not have to go through this definition every single time. You have a table of Laplace transforms, which we're going to talk about in the next video, which has in it many common ones, just like you don't have to go through the definition of the derivative every time you calculate a derivative. Same thing with Laplace transforms. So you won't have to go through it all the time, but it is helpful to remember that the Laplace transform is an integral, because those properties of integrals help you understand properties of Laplace transforms. Okay, let's do one other one using the definition. If I did not have to use the definition to find the Laplace transform of e to the t, I would look it up on the table. But the point is that those things that are on the table came from doing the definition and then writing it down in the table. All right, so Laplace transform of e to the t. Okay, so I can go ahead and simplify this. I can use a property of exponents. I'm also going to go ahead and rewrite the integral in terms of how that's defined, like I did in the last one. I'm going to replace that upper limit of integration, that is infinity, with b. All right, I can go ahead and combine those exponents. And since we're going to integrate with respect to t, I'll combine them and factor out a t. So I would add the exponents, so I would have negative st plus t, but then I'm going to factor out a t. Okay, so now we're going to go ahead and do this integral. Again, there's a u substitution I'm integrating with respect to t. I would let u equal the exponent. And so thinking about what you get for your du, you're going to end up with this factor of 1 over 1 minus s out front. So again, like the last problem, that works as long as that denominator is not 0. Okay, so I'm going to plug in my limits of integration, and then we're going to evaluate this limit. So now I need to go ahead and evaluate this limit. So again, I'm going to have to think a little bit about the sign of this right there to think a little bit about whether the first part of my expression, where the b is, right, I'm taking the limit as b approaches infinity, I'm going to need to think about whether that's an exponential growth function, so it's going to get bigger and approach infinity or negative infinity, or whether that's going to be an exponential decay function and approach 0. All right, so we said s cannot equal 1 over here. That's our split value here. So we're going to consider two different cases, s bigger than 1, s less than 1. And then we'll also go back and think about what happens if s is actually equal to 1. All right, so let's consider if s is greater than 1 first. If s is bigger than 1, then this exponent, 1 minus s, will be negative. So that first term in that limit, we will get 0, and then minus 1 over 1 minus s. So I get negative 1 over 1 minus s, or we can rewrite that as 1 over s minus 1. And again, that's for s bigger than 1. If s is less than 1, then that exponent I've circled there in pink will be positive, and so we will get infinity minus 1 over 1 minus s. So that will be infinity. And so our integral diverges. And if s is equal to 1, I have to go back up to the step right before I divided through by 1 minus s. So I need to go back to that step and think about that. So I'm going to get the integral limit from b as b approaches infinity of the integral from 0 to b of e to the 0, which is just 1 dt. And so I'll integrate that. I'll get t, and I'll plug in my limits of integration, and I'll get b minus 0, and so I get infinity. So that one also diverges. Okay, so just to kind of summarize that, then we can say that our Laplace transform of e to the t is 1 over s minus 1 when s is greater than 1. All right, and so in that next video, we're going to talk a little bit about how to use the table of Laplace transforms so that you don't have to go through this definition every single time.